Okay, so welcome to part 2 of our lecture on the solutions. So we derived so far the finite difference approximation for a first and a second derivative that we need to now go ahead and basically simulate an aquifer in Excel. Now, how does that work? So let's first start with doing a finite difference of the actual groundwater flow equation. So here at the top is one representation of that, right, in 3D. So now we have the X, Y, and Z directions, and of course we have a source term here, so it can be wetness, could be whatever, and then again the time difference on the right-hand side. So remember the Boussinesq equation for the leaky confined aquifer with leakage, for example. Now, if we consider a simple case of steady state again, and no leakage or no source term, we end up with that very simple equation in 1D, which is basically the Laplace equation, right? This is just the second derivative is 0, and that's it. Now, in 2D, if we do d squared h dx squared plus d squared h dy squared equals 0, this is our simplest case, if you will, for a 2D approximation. So we're going to solve this in 2D using finite difference and then put it in Excel. Okay, well, we just did derive those second differentials using the Taylor series expansion. So if you go back to that slide, you can see where those come from, but that's basically exactly, copying from that slide the value. So now we know exactly what the equation is. Now what we want to know is Hij, right? So we can approximate the head in our cell right now. So let's say now our whole domain is separated in a grid, right? In little squares or little rectangles, whatever. So if we want to solve what is the head here now, or here actually in X and Y, what is the head at X and Y? Well, the head at X and Y, you can see here that you can put this on the left-hand side and put everything else on the right-hand side, right? And now we can actually solve for it, right? We can solve for the head at X and Y. Now, if we're saying that dx equals dy, so let's say we have a square grid just for simplicity, right? Let's say we choose that our grid size is 100 meter in the X direction and 100 meter in the Y direction, right? So all our cells are the same. So now delta X equals delta Y, right? So these two things are the same number, so it doesn't matter when we do the math, right? So now what we have is, now you can see that if we, again, solve everything, we can see that the head here at X and Y equals the head and the head at X minus 1 and Y plus 1 and X, Y minus 1 and X divided by 4. In other words, if you look at what this is, right, this is literally the average of the 4 neighbors. So again, for the simplest case where, hydraulic conductivity is homogeneous, where it's a steady state equation, there is no recharge, so the simplest case, and the grid is squared, right? And so we have the same delta X and delta Y. The result is that basically we just need to do the average of the 4 neighbors. That's amazing. That's so simple. Now, if the hydraulic conductivity field is not homogeneous, and we've dealt with that in the last lecture at length, right? Now, in the finite difference, that means we need to carry it. And again, here I derive everything, but we start, like always, with our Darcy flux, right? So we say Darcy flux, the change in Darcy flux is 0 if the change in k dh dx is 0. But now, again, we're back to a problem similar to the one with the unconfined aquifer, where now our hydraulic conductivity is actually a function of x. So we can't just say it's a constant, because it's not. So how do we deal with that? Well, we just carry it in. So again, look at, so this thing ddx, the first ddx, right? We know how to deal with it. That's just the first derivative of this whole bit. So if we write it in finite difference approximation, again, go back to that slide, we can write it this way, right? So it's k dh dx, I plus, instead of 1, I put 0.5, doesn't matter. We can expand, to plus 1, plus 2, 0.5, whatever. So here I'm just expanding it to, half the distance. And then look at that. Now we have dh dx in here, which again, we can use the finite difference approximation to expand, which is what we do down here, right? So again, we can use our finite difference approximation to expand the whole thing with the k carried inside. And if we do all this, so again, this is like the same equation where we isolate h at I. Again, this is in 1D just so you can follow kind of the steps on this slide easier, right? But now if we go up to 2D, right, so the j, right, the y side is going to be the exact same expansion, the same principle, and now we can have an expression for our head in x and y, right, which is basically the weighted average of the four neighbors. So again, if you follow all this, this is I plus 1j, right, I minus 1j, like we were saying before, ij minus 1, and then ij plus 1. So these are the four neighbors, but now the head in each cell is weighted by the hydraulic conductivity. And this is how we carry heterogeneous domains in finite difference approximation. So now let's look at the simplest example you can find on the internet. Right here, this is a 2D aquifer in Excel, and if you look at the Excel formula up top here, you can see that this is literally the formula in each of those cells is the average of the four neighbors. That's it. This is the whole code, right? So obviously we have a no slip boundary, no flux boundaries at the top and at the bottom, right? That big red line means there's no water going, from the top down or from the bottom up. And on the left and on the right, we have 10. Sorry, I'm going blurry again. We have 10 here and 15, at the high side. Now I play with the code, so here I'm clicking on some cells, right, to add fixed level. So instead of carrying that finite difference, I'm just saying, okay, this cell is at 6 meters and that cell is at 25 meters here. So these are fixed cells and they're sort of mimicking wells, right? So when we do wells, you can see here that sort of halo around, right? So if we pump down to 6 meters, this is what your piezometric surface would look like, right? So what we're looking at is a top-down view of the piezometric surface. So it's similar to those piezometric maps that we had before, right? Where we saw here, if it was an injection well, for example, you can see we have a higher, so we have a bump. Here we have a bump high in the piezometric surface, right? So we have a high spot because we're injecting water, and we have a low spot here because we're pumping water out. And again, this is sort of an introduction to our lectures on wells hydraulics that will come in the next module. And finally, one more example with a heterogeneous field, right? So this is the exact same setup as before. Same boundary conditions on the left and right, on the top and bottom. Same two wells here, but now we have a heterogeneous K field, right? So now you can see that formula up top, which is the weighted average of the four neighbors, right? So each formula has the weighted average of the neighbors. But you can see here that we have something that looks like this, right? So there's a low permeability band here in the middle that resists flow. So you can see that, the whole piezometric surface is different from before. And again, those Excel files obviously will be provided to you so you can see how they work. Now, finite difference in Matlab, and again, this is the same thing, but another example. So let's say we want to simulate a dam here, right? This is the dam, and there's a reservoir at the back and a river here. So we would know what the boundary conditions are here and here. And again, by doing finite difference, so you can see here the equation, now we have a x and y are different. So now it's not just the neighbor, the mean of the four neighbors, because the x and y grid may not be the same. So we're carrying those dx squared and those dy squares, right? So now we actually have a proper equation for the finite difference. But again, you can see that all I'm doing is calculating the head at I and j, and this is just our finite difference approximation. And we do this on a loop until things are consistent, just like we did in Excel. And now we can actually, this is quite powerful because now we can actually reproduce or find what the flow net, so that's what we call a flow net, and it's sort of similar to a piezometric map, but it's a 2D slice, right? So now we can see the equipotentials are, downwards here, and the flow lines, right, are here with the arrows. And again, this is a very, very simple code, and this is exactly what Modflow, for example, the USGS package, right, does. I mean, this is exactly the same that they do, with those engineering tools. Now, for unsteady flow, I'm just making a note here because we haven't talked about unsteady flows much at all. But when you do pumping, this is all it is about is unsteady, because when you start pumping, right, you're dropping that water table down, or piezometric head down, and then if you stop pumping, it goes back up. So really the time evolution of the water table is what tells you what the transmissivity of the aquifer is, and tells you a lot of information. So Wells tests are in essence unsteady. Anyway, so when we do the finite difference for unsteady equation, so dHdt, same thing, right? All we have is now we have dHdt on that right hand side. Well, all we do is write down the finite difference approximation for dHdt, which is h at t plus 1 minus h at t divided by 2 delta t, right? Or divided by delta t, excuse me. So again, if you do that and you write it all out, now you have an equation with the time variable in there. So it's just the same as we did before, except now we also have the time, but we can find what is the head at I, so this is a 1D version just for simplicity again, but what is the head at X at the next time step, so we can predict in the future, right? And iteratively we can solve those equations with finite difference methods. And finally, I leave this as an example of what we deal with here in the Midwestern of the US, which is the breadbasket, right, of the US and the world. We grow a lot of corn and some soybean, but mostly corn, right, a ton of corn. And the way people drain their field is by using tile drains, right? So what they want is you can see here this undrain and drain condition, right? So we use tile drains to drop the water table so that there's more basically room for the roots to grow and better production in the fields. And this on the left-hand side here is a little model of that you guys can, following the steps here, highlighted here, you can actually write the dH squared. Now this is an unconfined situation. So if you go back to the unconfined lecture with recharge, right? So W is the recharge. So this is something we've done before, and we've solved it analytically. So you have a solution in the drainage lecture for this equation, right? But you can also write a finite difference equation for it, following the steps in this lecture. And this is an example here on the bottom left of an Excel file that does just that. So in red is the numerical equation, and you can see it's an exact match to the analytical solution. Okay, I think I will leave it here. So this was the last, official lecture of content. So this is a lot to unpack in this lecture, but that gives you a taste, excuse me, of what can be done with those, methods of solution of those groundwater flow equation and things you can calculate, such as the water table elevation, in a cornfield, for example, or if you have a huge heterogeneous, aquifer, like how do you predict flow to the river or flow after the rain, so on and so forth. So we've seen really all the critical equations that you can solve with finite difference methods. Okay, thank you.